For months, 3i Atlas was a blur of numbers, plots, and distant images racing through the solar system at an almost absurd speed. Interesting, yes, but still abstract. And then, suddenly, everything stopped. Not the object itself, it never slowed down, but the conversation around it did. Telescopes went blind at the worst possible moment. Data streams froze, speculation exploded. And when the object finally re-emerged from behind the sun, it wasn't the same thing we thought we were tracking before. The chemistry had shifted, the brightness had surged, the color had changed, and signals we had never detected from an interstellar object before were suddenly there. This wasn't just a flyby anymore. This was a stress test of everything we think we know about objects born around other stars. And what 3i Atlas revealed forced astronomers to pause, reassess, and in some cases, completely rewrite their assumptions. By October, the world was finally ready to study 3i Atlas properly. It had grown bright enough, close enough, and active enough for detailed analysis. Ground-based telescopes had tracked its strange molecular ratios, watched it change color twice, and even hinted at a mysterious sunward-facing feature that sparked intense debate. And then, just as the most critical phase approached, the sun got in the way. From Earth's perspective, 3i Atlas vanished behind solar glare exactly when it was about to experience the most extreme heating of its entire journey. This was the moment when comets either flare dramatically, fragment under stress, or reveal what they are truly made of. Instead, Earth went blind. For weeks, no optical telescope on the ground could see what was happening, leaving a dangerous gap where speculation thrived and certainty evaporated. But while Earth couldn't see, the solar system could. Scattered across space, a fleet of spacecraft were perfectly positioned to watch the encounter unfold from angles we rarely get to use. Coronagraphs aboard Stereo A, SOHO, and the newly launched GOES-19 blocked out the sun's disk, creating artificial eclipses that revealed what was happening just beyond the glare. When researchers later combined this data, the result was startling. For months, 3i Atlas had been brightening steadily, following a fairly normal cometary trend. Then, inside about 2 astronomical units, the curve didn't just steepen, it snapped upward. Brightness began increasing at a rate that defied standard comet models, indicating a violent surge in mass loss. This wasn't gradual sublimation anymore. Something inside the object had switched on. Before disappearing behind the sun, 3i Atlas had already given a warning that it was no ordinary comet. Using the Swift Observatory, NASA detected a massive surge of hydroxyl radicals, the fragments left behind when sunlight breaks apart water molecules. At nearly 3 times Earth's distance from the sun, where temperatures are still brutally cold, 3i Atlas was dumping water at roughly 40 kilograms per second. That is an extraordinary rate for such a distant object. More like a fire hose than a slow leak. Standard models say water ice should not behave like this so far out. The implication was unsettling. Instead of gently sublimating from the surface, 3i Atlas appeared to be ejecting icy grains into space, massively increasing the surface area and supercharging its activity. And then, just as we were beginning to understand the scale of what was happening, the object slipped behind the sun and vanished from view. When 3i Atlas finally emerged from behind the sun, it wasn't just brighter, it looked different. For months, it had appeared red, typical of dusty, organic-rich surfaces. Later, observers on Earth saw it turn green, a sign of specific gases fluorescing in sunlight. But the solar observatories saw something else entirely. Through specialized filters, the comet appeared distinctly blue relative to the sun. That blue hue is the fingerprint of volatile gases like carbon monoxide and amide radicals, signaling that the intense solar heat had stripped away the dusty outer crust and exposed a violently outgassing interior. In other words, the comet we thought we were studying before wasn't the real engine at all. Only after surviving the sun's closest approach did 3i Atlas reveal what it truly was beneath the surface. Just before its solar encounter, 3i Atlas performed a quiet but extraordinary maneuver. It passed just 0.19 astronomical units from Mars, close enough to turn the red planet into a front-row seat for history. This was a rare stroke of cosmic luck. For the first time ever, an interstellar object would be observed not just from Earth or orbiting telescopes, but from the vicinity of another planet. NASA's Mars Reconnaissance Orbiter immediately redirected its high-risk camera, a system powerful enough to spot objects the size of a coffee table from hundreds of kilometers above Mars's surface. If anything was capable of resolving the nucleus of 3I Atlas, this was it. Expectations skyrocketed. Scientists hoped to finally glimpse the solid heart of this visitor from another star. But when the images were eventually released, weeks later, they told a very different story. Instead of a sharp nucleus, HiRISE saw a fuzzy, unresolved glow, a dense shroud of gas and dust stretching roughly 1,500 kilometers across. The nucleus was still hidden, buried inside its own violent activity. Paradoxically, this failure to see the core became data itself, helping constrain the size of the object and confirming that whatever was happening around 3I Atlas was both intense and deeply obscuring. Mars orbiters were not alone in witnessing this passage. ESA's Mars Express and ExoMars missions also captured the event, while NASA's MAVEN spacecraft used its ultraviolet spectrograph to image an enormous hydrogen envelope surrounding the comet. This cloud extended far beyond the visible coma, revealing just how aggressively 3I Atlas was shedding material. And then came a first in the history of astronomy. On the Martian surface itself, the Perseverance rover turned its Mastcam Z toward the sky. In long-exposure images, 3I Atlas appeared as a faint, ghostly streak drifting among the stars. It was subtle, almost unimpressive at first glance, but its significance was enormous. This marked the first time humanity had ever observed an interstellar object from the surface of another planet. A visitor from another star system, seen not just from Earth, but from Mars. The implications were profound. This was no longer a distant curiosity. 3I Atlas had become a multi-planetary observational target, leaving signatures across the solar system as it passed through. As 3I Atlas emerged from behind the Sun in November, the astronomical community held its breath. The brightness surge observed during perihelion was so extreme that some models suggested the comet could not possibly survive intact. Harvard astrophysicist Avi Loeb publicly raised the possibility that the object had fragmented, perhaps even exploding into 16 pieces. If true, this would have meant the end of any hope to study a coherent interstellar nucleus. The fear was understandable. The mass loss rates implied by the brightness increase were enormous. To sustain that level of activity, the object would need to shed material at a pace that would destroy most known comets. For days, uncertainty reigned. Had we just lost the most valuable interstellar visitor ever detected? But as new observations came in from the Lowell Observatory and the Virtual Telescope project, the panic began to fade. The data showed no debris train, no chaotic swarm of fragments. Against expectations, 3I Atlas had survived. The apparent explosion was not a breakup, but an intense shedding of its outer layers. The nucleus remained whole, suggesting it was far denser and structurally stronger than a typical comet. Survival did not end the controversy. In fact, it intensified it. Avi Loeb and others argued that the object's behavior still showed anomalies difficult to reconcile with natural explanations alone. Two features stood out: a persistent sunward jet and what appeared to be non-gravitational acceleration, keeping the object on an unusually straight trajectory. Loeb suggested that the thrust required to produce this motion via natural outgassing would be immense, potentially exceeding what the observed gas cloud could supply. If the thrust wasn't coming from natural sublimation, then something else had to be considered. The idea of artificial propulsion re-entered the conversation, not as a conclusion, but as a provocation. In response, other researchers pointed out that sunward jets are not unheard of in comets, and that non-gravitational acceleration is a well-documented result of asymmetric outgassing, the so-called rocket effect. What made 3I Atlas different was not that these features existed, but that they existed simultaneously, at extreme levels, in an interstellar object. The community found itself divided, not over what was observed, but over how much weight to assign to each explanation. And hanging over the debate was one unresolved question: could upcoming observations finally settle it? For weeks, the debate circled the same question. Was 3I Atlas just an unusually active comet, or was something more exotic pushing it along? Optical images were striking. chemical hints were provocative, but dust and glare always leave room for doubt. Then radio astronomy entered the scene and changed the tone entirely. The Meerkat radio telescope array in South Africa detected faint but distinct absorption lines at 1,665 and 1,667 megahertz, the unmistakable signature of hydroxyl radicals. Radio waves don't care about dust. They pass straight through the thickest comas, revealing what's actually there. This detection mattered because hydroxyl is the smoking gun fragment of water. It confirmed, beyond reasonable doubt, that 3I Atlas was venting water vapor in large quantities. This was the first time radio emissions had ever been detected from an interstellar object, and it instantly grounded the conversation. Whatever else this object might be, it was undeniably wet, icy, and chemically familiar at a fundamental level. The most extreme speculation lost its footing, not because the object became boring, but because the evidence became sharper. With water confirmed, attention returned to the object's motion. Avi Loeb had argued that the observed acceleration seemed too clean, too straight, to be explained by natural outgassing alone. But a new dynamical study modeled 3I Atlas's trajectory over the past century and found something crucial. The acceleration was entirely consistent with the rocket effect produced by the observed mass loss. When a comet ejects gas asymmetrically, it behaves like a natural rocket, gaining a small but measurable push. In a hyperbolic orbit, moving at extreme speed, that push appears even more linear than it would for a captured comet. Perspective matters. Reference frames matter. Once those were accounted for, the motion of 3I Atlas followed Newton and Kepler precisely. The object wasn't defying gravity, it was obeying it in a regime we rarely get to observe. What had looked like controlled propulsion resolved into extreme but natural physics, driven by the same water loss Swift and Meerkat had already confirmed. With the propulsion debate cooling, a deeper question took its place. For years, astronomers assumed interstellar objects would be pristine time capsules, perfectly preserved relics from their parent star systems. A new paper challenged that assumption head-on. According to this research, 3I Atlas is not pristine at all. It is, in a very literal sense, cooked. For billions of years drifting between stars, the object was bombarded by galactic cosmic rays from supernovae and active galactic nuclei. These high-energy particles penetrate meters into ice, breaking chemical bonds and reshaping the material from the inside out. Over immense timescales, this process converts water and carbon monoxide into carbon dioxide and complex organic solids, forming a radiation-processed crust roughly 15 to 20 meters thick. What we are seeing now is not the primordial heart of 3I Atlas, but that processed outer layer peeling away under solar heat, like a sunburned skin finally flaking off. This cooked crust explains something that had puzzled observers from the beginning: the extreme abundance of carbon dioxide relative to water. In typical solar system comets, water dominates and CO2 plays a minor role. In 3I Atlas, the ratio was flipped dramatically, nearly 60 times higher than expected. But the chemistry goes deeper. Spectra revealed nickel and iron gas in the coma, with a nickel-to-iron ratio unlike any comet previously observed. These metals matter because they act as catalysts. When water melts inside the porous crust and comes into contact with metal grains, exothermic reactions can occur, releasing heat. That heat melts more ice, increases pressure, and eventually ruptures the surface, producing violent jets of gas and dust. This process, known as cryovolcanism, creates a feedback loop powerful enough to explain the brightness surge, the sustained jets, and the object's surprising resilience. 3I Atlas wasn't burning fuel or firing thrusters. It was running a natural chemical engine forged by billions of years in interstellar space. Once nickel and iron entered the picture, the story of 3I Atlas took a decisive turn. These metals are not just passive contaminants drifting in the coma, they are active players in chemistry. When water ice melts inside a porous crust and comes into contact with metal grains, it can trigger exothermic reactions, processes that release heat instead of absorbing it. This is not speculative chemistry. These reactions are well known on Earth and in laboratory settings. Inside a comet, however, they create something far more dramatic. Heat melts more ice. More ice releases more gas. Pressure builds beneath a rigid, radiation-hardened crust. Eventually, that pressure finds a weak point and the surface ruptures violently, ejecting gas and dust in a focused jet. This feedback loop can sustain activity long after simple solar heating should have faded. It explains the brightness surge, the persistence of jets, and why the object didn't fragment despite shedding enormous amounts of mass. The comet wasn't falling apart. It was venting. Many models predicted that the intense mass loss during perihelion would destroy the nucleus, and yet it didn't. The survival of 3I Atlas is itself a critical data point. A fragile rubble pile would have disintegrated under that stress. Instead, the nucleus remained intact, implying significant internal strength and density. This aligns perfectly with the idea of a processed crust, chemically altered and mechanically reinforced by billions of years of cosmic radiation. Rather than weakening the object, interstellar space may have hardened it. What looked like an impending explosion turned out to be a shedding of layers, not a catastrophic breakup. The comet emerged altered, scarred, but structurally sound, having endured conditions that would have destroyed many solar system comets. As 3I Atlas races away from the Sun, one more major encounter lies ahead. In March 2026, the comet will pass about 0.35 astronomical units from Jupiter, close enough to enter the planet's Hill sphere, the region where Jupiter's gravity dominates over the Sun's. This is not a capture scenario. The object is moving far too fast for that. But it is a final gravitational stress test. Jupiter's immense gravity will subtly tweak the comet's trajectory, potentially altering its rotation or triggering new internal stresses. Crucially, this encounter may be observable. If NASA's Juno spacecraft remains operational, it could offer a last close-up view of this interstellar traveler from the outer solar system. This flyby represents the final opportunity to study how an object forged between stars responds to the most extreme gravitational environment our planetary system can offer. By this point, something important has already happened, regardless of what comes next. 3I Atlas has fundamentally changed how we think about interstellar objects. It has shown that they are not pristine fossils drifting unchanged through space. They are processed, altered, chemically active bodies shaped by cosmic radiation, time, and extreme environments. It has demonstrated that small objects can carry complex chemical engines capable of driving violent activity without artificial intervention. It has revealed that the space between stars is not empty, but transformative, a place that cooks, hardens, and rewrites the material passing through it. Long before it leaves our solar system for good, 3I Atlas has already forced astronomers to update their assumptions, and that impact will outlast the object itself. So this is where the dust finally settles, not because the mystery is gone, but because the picture is finally sharp enough to understand what truly happened. 3I Atlas did not turn out to be an alien spacecraft, and it did not break the laws of physics. But it did something far more important. It forced us to stop, to pause our assumptions, to confront how incomplete our mental models of interstellar objects really were. For a brief moment, as it raced through the inner solar system, 3I Atlas became a perfect experiment. Blinded Earth-based telescopes missed its most violent phase, but spacecraft across the solar system watched instead. From solar coronagraphs to Mars orbiters, from ultraviolet spectrographs to radio telescopes, every layer of observation added a new piece to the puzzle. We saw water pouring out like a fire hose where it shouldn't. We saw brightness surge beyond standard comet behavior. We saw color shifts that revealed a hidden interior. We detected metals acting as chemical catalysts. We confirmed radio signatures that ended the propulsion debate. And slowly, the story transformed. What emerged was not a pristine relic from another star system, but a survivor. An object cooked by billions of years in interstellar space, hardened by cosmic radiation, chemically reworked, and carrying a processed crust capable of powering violent activity through natural feedback loops. The sun did not destroy it. Instead, it peeled it open, exposing the consequences of an interstellar lifetime. And that is the real revelation. Interstellar space is not a museum. It is a furnace, a place that changes objects fundamentally before they ever reach us. 3I Atlas has already changed astronomy. It has shown us that interstellar objects are not just faster versions of comets we already know. They are a different population entirely, shaped by environments we are only beginning to understand. It has taught us that extreme behavior does not require exotic technology, only time, chemistry, and physics operating over unimaginable scales. And it has reminded us that even when speculation fades, wonder does not. Soon, 3I Atlas will leave the solar system forever, carrying its scars and secrets back into the dark between stars. But the questions it raised will stay here. The models will be rewritten. The next interstellar visitor will be watched earlier, harder, and with fewer assumptions. And when that next object arrives, we will be better prepared, not because we solved everything, but because this one forced us to listen. If you want to keep following discoveries like this, moments when the universe quietly reshapes what we think we know, make sure you're subscribed. Because the next time something from another star system passes by, it may not stop the world in the same way, but it will almost certainly surprise us again.